Okay, the last thing we're going to do with the polynomials is this idea about multiple roots and how we can investigate a bit further with multiple roots. Now, it turns out that if a polynomial has a root of multiplicity m, then its derivative will have the same root but of one less degree. So if it's a double root, then in the derivative it'll be a single root. If it's a triple root, in the derivative it'll be a double root, but therefore it also means that if you differentiate it a second time, it'll be a single root of that second derivative, and so on. So it's a way of finding multiple roots. Let's prove it. So what I'm saying is, our polynomial has a factor, and it's a repeated root, so it's power of, well, I put m there. Now, to specify it, m has to be greater than 1, and also x equals a is not a solution of this other factor. Otherwise, the multiplicity would change. So let's differentiate. Write down the first, so we've got x minus a to the m. Diff the second, well, the best I can do there is just say q dash x, plus write down the second, qx. Diff the first, but I'm going to have to use my chain rule to diff the first. So bring down the power, m, lower the power, m minus 1, diff the inside 1. Now, if we have a look at all that, there is indeed a common factor of x minus a, and we always factorise out the lowest power. So we'd have x minus a to the power of m minus 1, and then, well, the second product would be some sort of polynomial if we were to expand that all out. So I could just say, okay, it's times some other polynomial, which I've called Rx. So yes. Oh, and we also know that A is not a solution to Rx because, well, it is a solution to the first half, the x minus a part, but we've specified it's not a solution to the Qx, so that therefore, when we add them together, just highlighting that, therefore, when we add them together, well, x minus a is not going to be a common factor of both of them. So, yep, the derivative will also have a solution at x equals a, and its multiplicity will be one less than the original polynomial. Oh, that kind of helps us because we have to solve this equation, but we know it has a double root. See, cubics are harder to factorise than quadratics. So if I know it's got a double root, the trick is let's find that first. So there's our polynomial. If I differentiate it, I end up with a quadratic, which is easier to solve. So I can try and find that double root using the derivative. It factorises to be 3x plus 1 and x minus 3. So one of those will also be a solution to our original equation. So either x equals minus a third is going to be a solution, or x equals 3 will be a solution. Which one do you think is more logical to be the solution, looking at the equation we're trying to solve? Yeah, look, the reason logically I would go to x equals 3, you see how it's a monic? So it's unlikely that 3x plus 1 is going to be a factor of that. I mean, it could be, because I might have a third out the front as well. But it's more likely that x minus 3 is going to be the factor. But it's easy enough to check. So I now know it's x minus 3 squared. The other factor then I can work out by logic. Constant times the constant is going to give me the constant. Well, minus 3 squared is 9. Therefore, 2 must be the constant in the other one. And so now I can solve it. X equals negative 2 or x equals 3 is the solution. This also brings up an interesting point. Had the question said, instead of saying solve the equation, said find the zeros, then my answer would be not negative 2 and 3. My answer would be negative 2, 3, and 3. Right? Because it's a double root. That's the difference between solutions to the equation and the zeros itself. Let's have a look at the 1991. You see, I really like the 1991 because 1991 is palindromic. So that's always neat. But then have a look at the polynomial. It's palindromic as well when you look at the coefficients. See, look, it goes 1a, b, a1. So I don't know whether they did that on purpose because it was 1991, but I thought that's kind of neat. And where 2 plus b squared does not equal 4a squared. what? That'll come into play later. It'll be obvious why later. At this stage, we're sort of going, well, who cares? That 2 plus b squared can't equal 4a squared. We shall see why later on. Right, so alpha is a root. First thing they want us to show is that it can't be 0, 1, or minus 1. Well, let's use our factor theorem. If I sub in 0, I get 1. So yeah, it doesn't satisfy the factor theorem, so 0 can't be a solution. Sub in 1, I get 2a plus b plus 2. Well, I can't say whether or not that's 0 because I don't know what a and b are. So let's have a look at the other one. Polynomial negative 1 is minus 2a plus b plus 2. But again, I don't know whether that's going to be 0 or not. Now that's where the piece of information is going to come in handy. They've told me that 2 plus b all squared is not equal to 4a squared. Therefore, 2 plus b is not equal to plus or minus 2a. So plus or minus 2a plus b plus 2 is not equal to 0. So I now know that plus 2a plus b plus 2 can't equal 0. And I know that minus 2a plus b plus 2 can't equal 0. So now I know for sure that polynomial 1 and polynomial negative 1 can't equal 0. Therefore, they can't be solutions either. Now it wants us to show that the reciprocal of alpha is also going to be a root. So I'm going to use the factor theorem again. Well, let's turn it all into one fraction. Let's see what happens. If I turn that all into one fraction, the common denominator is alpha to the power of 4. And on the top, I get 1 plus a alpha plus b alpha squared plus a alpha cubed plus alpha to the power of 4. But the top of the fraction is what I get when I substitute alpha into the polynomial. And they told me that alpha is a solution, or a root. So therefore I know polynomial alpha is equal to 0. Thus, polynomial 1 on alpha is equal to 0. So for this equation, every time we see alpha as a solution, 1 on alpha has to be a solution as well. Okay. So every time alpha is a root, 1 on alpha is going to be a root as well. In fact, that particular result will always hold true when you notice the coefficients of the polynomial are palindromic. That'll always be true, that if alpha is a root, 1 on alpha will also be a root. Now, deduce that if alpha is a multiple root, then its multiplicity has to be 2. So it has to be a double root. And just for the fun of it, 4b has to equal 8 plus a squared. Okay. So we just said if alpha is a root, then so is 1 on alpha. Therefore, logically, if alpha is a double root, so if we see alpha appearing twice, 1 on alpha must appear twice. So we now know 4 roots of our equation. But our polynomial is a quartic. And we know that has a maximum of 4 roots. So there are no more. So therefore, it would be impossible to have a solution or a root with multiplicity greater than 2. Another way of thinking about it is, say alpha was a triple root. So alpha would appear 3 times. Well, therefore 1 on alpha would appear 3 times. That would give me 6 solutions. But I can't have 6 solutions for a quartic. So that's another way of thinking about it. Because there's a maximum of 4 solutions, then I've got a maximum of 4 roots. All right, now the other interesting bit, proving that bit of algebra. And I'm going to do that via the derivative now, because I know it has multiple roots. If alpha is a solution to the polynomial, and now that we know it's a double root, it will also be a solution to the derivative. And the same for 1 on alpha. Okay, there's my derivative, 4x cubed plus 3x squared, 2bx, and a. So the roots, I know alpha is going to be a solution to this cubic, because it's a double root. I know 1 on alpha is going to be a solution to this cubic, because it also is a double root. And there must be a third solution. I'll call it beta. Now, it won't be a solution, beta won't be a solution to the original polynomial, but the derivative must have a third root in there somewhere. Okay, let's play with sum and product of roots. So alpha plus 1 on alpha plus beta will be minus 3/4 a. So that's from the sum of the roots. 2 at a time. Well, the alpha times the 1 on alpha will give us 1. And then we'll get plus alpha beta plus beta on alpha. That'll be a half b. So that's the sum of the roots 2 at a time. And what the heck, let's do 3 at a time. And that actually locates beta for us, because the alpha times the 1 on alpha will give us 1, and then we'll multiply that by beta. So we get beta is minus 1 on 4. Well, a quarter a. 3 at a time. So, all right, what are we trying to prove again? It was on the page before. Oh, no, there it is up the top. 4b is 8 plus a squared. Well, now that I know that beta is minus 1/4 a, I can eliminate beta out of the other two. And then I'll have simultaneous equations, and I can get rid of the alpha. So let's do all that. Substitute the third one into the first one. So alpha plus 1 on alpha, but instead of saying beta now, I'm saying minus 1/4 a. That'll be minus 3/4 a. So alpha plus 1 on alpha is minus a half a. Okay. Now, if I put it into the second one, I get 1 minus 1/4 a alpha minus 1/4 a 1 on alpha is a half b. But I can group the minus 1/4 a outside of alpha plus 1 on alpha. Over here, on the left-hand side, I said alpha plus 1 on alpha is minus a half a. So I can substitute that in. That eliminates the alphas. Now it's just a matter of playing with the algebra to get what we want. So 1 plus an 8 a squared equals a half b. Multiply everything by 8, and we have the result that they're looking for. All right, now, a little note here. If a tangent to a cubic has 2 solutions only, it means you've got something like this. It means it must be a tangent here, and then it cuts the cubic somewhere else. So it has 2 solutions. So it's not like a circle where a tangent only touches the circle in one spot. It is possible for a tangent to cut a cubic twice, because it'll be a tangent in one spot, but then it'll cut it somewhere else.